Okay, hello everybody. So this is the final lecture of the course, and what we're going to look at today is the idea of reduction, dimension reduction in particular. So last week we looked at clustering, which is a crucial visualization technique for understanding large-scale data-intensive applications. So particularly, it helps us to do segmentation of the data that isn't done manually. Okay. We also saw in lecture 6 how to cope with multiple dimensions. So we used bubble plots for 3 dimensions, radar plots for if there's a few more. We could also use comparative bar charts as well. But for really data-intensive applications, these may not be enough, okay, to understand what the results are telling us. So this week we're going to look at a technique called dimension reduction or dimensionality reduction to help understand the structure of the data. And we'll be using things that we're familiar with already. So in particular, scatter plots for the structure and then radar plots for the interpretation. It's not the only way of doing these things, but that kind of goes a bit beyond where this course is aimed at. So this is a visualization course. The dimensionality reduction is more of a machine learning technique, and if you need to find out more about it, then you probably need some more machine learning information. Okay, so what is dimension reduction? Well, as you may have guessed, some of these data-intensive applications have far too many variables to get a sense of the shape or the structure of the data. So as we saw, we can deal with 3 dimensions in bubble plots. Radar plots give us about 6, or actually at the end of the last lecture we had about 10 in radar plots. But what if there's 300 or 600 or 1,000? It's just impossible to try and get a sense of the data with those kind of dimensions. So dimension reduction is a way of embedding the data often into 2 dimensions, so we can look at the structure. And a popular method for doing dimension reduction is called principal component analysis. This was quite an old technique, actually invented in 1901, but it's really linear. It seeks to kind of look at where's the main action going on in the data, and then align the axes with that main action, and then map that down onto the 2-dimensional plane. So it's not ideal for coping with complex data. It's still very useful, and people will still use this very commonly, but I haven't really got time to cover that, so we won't talk about that. What I'm going to look at today is a technique called T-distributed stochastic neighbor embedding, or TSNE. And it's often, if you've got really high dimensional data, it's often used in combination with PCA. So if you've got maybe several hundred dimensions, you can use PCA first to get that. Will kind of get rid of most of the redundant dimensions. So when I talk about redundant dimensions, they're variables that aren't really telling us anything about the data structure or the data. They don't really have any impact on any other variables. So we can get rid of some of them using PCA, and that can bring it down to say 50 dimensions, and then use this TSNE technique to reduce to 2 dimensions. We're going to focus on the TSNE because I think it's the more interesting, more timely of the 2. But I guess if you're a full data scientist, you probably would use both. Both are included in the scikit-learn library, so you can import the PCA module and the TSNE module from scikit-learn, different parts of scikit-learn. Okay, I'll finish that video there, and then we'll look a bit more about what it does.